Okay, students, let's begin lecture. We're going to talk about one of the homework exercises that I know tripped up a bunch of you. We're going to try to enforce it, some of the concepts, and then I'll see about maybe redoing it on another homework over the weekend, just so you have some extra practice. But before we do that, I want to have a short discussion about discussions. I love to see you guys put discussions concerning homework problems on the discussion board, because it is a very, it helps you just writing down something. And then hopefully somebody like Darian or maybe me or one of your classmates will chip in and give you some tips and that will help. That will help them and it'll help you as well. So I highly encourage that. There's a couple things I want you to try to do. Now, are you watching? Because there's something you have to see. Army man, are you? Okay, good. Make sure you watch this. Everybody watch this. Because there's a couple things of discussion I want to bring to your attention. Now, here's a fairly nice discussion thread. I don't remember whose it was. It has a good title. You want to have a good specific title. You don't want to just have, help me. Although that is going to get attention, somebody might not really care that much about you as a person. But if you put down the homework problem and a little description of it, like even just saying question 5, that's good. And that way, if somebody's stumped on question 4, they can bypass this. If they see question 5, if they're stumped on question 5, then they can lock in. All right. Another thing that I want to draw your attention to is down here. All right, down at the bottom. All right, so where it says allowed threaded replies and allow liking, yeah, this stuff, I want you to start checking that. And some of you have been, but I've noticed a lot of you, and I don't think I gave you a whole lot of instruction on it till today, so I want you to start doing that. It'll look something like this. When so type in whatever your discussion question is, and then are you watching? Yo, in the back. Good. You see it? Okay, make sure you look. Get your head out of your phone. Take a look. This is what we want. We want allowed threaded replies, and we want to allow liking. And if we do that, then these discussion threads will become extremely efficient. All right? And you know what? I have about 500 students this semester, and I'll just give you a little tip. Sometimes a student they won't post in discussions, or they can get really fast attention. They'll send me a message, and then they won't realize, they'll ask me something about question 5 on homework 6, and they won't realize that there was already 2 threads about it, 2 different threads, but they didn't read it, right? So when that happens, or when another popular one is, what's the date of the exam, the next exam? All you got to do is check syllabus on that, right? So when that kind of thing happens, I frequently give you guys a very brief reply, and some might say terse, check syllabus, check discussions, 2 words. All right, and that's what. But if you start doing this, you don't have to bug me with personal messages, all right? That I might not get to for a couple hours. If you start in discussions, and if you don't get help, then post your own question. That's a good strategy. All right, that'll work really well. And the discussion threads that you do in this way can be like little study groups, little virtual study groups, and it can be very effective. Right now, I want to bring up something else that I want to draw your attention to that I've never noticed before, but I now know it can happen, and that is a homework question. The question was fine. Everything about it was fine, except for one little thing. Down here it said this topic was locked, and the student didn't, even I didn't see it. Because when it gets locked, the web courses pushes it down to the bottom of the list, and I don't even look at it. All right? I don't see it unless I'm diligent like I was this morning. So this particular student inadvertently, they were down here, and they did threaded replies. They didn't do allow liking, but here's where they made their mistake. Okay? They put a until date. Don't do that. Just leave that blank. All right, so this thing here, leave that blank, and that'll be, it'll just keep your thread open until the cows come home, until the end of the semester, so it'll be much more helpful. It'll eventually descend down the list, but this one was a homework 6 question, but after, a few hours, bam, it was down at the bottom of the list, and nobody's going to see it. So. All right, now questions about discussions. Okay. Let's talk about the brain burner on homework 6. You might want to take notes. All right, and I know I got tripped up, a few of you got tripped up on it. Let's just go over it. And actually this is the strategy that I developed after talking to one of the online students in the online section. And here's the problem. Brain burner, question number 5. And eventually this will not be a brain burner for you guys. You guys will be able to knock this one for a home run every time. But for this stage of the semester, it's a little bit trickier than stopping time. Now this one, I know some of you might be tempted to figure out a stopping time, but notice this one doesn't ask you for the stopping time, and that's nice. You can get a stopping time from it, but it's asking about stopping distance. So if you answer the number of seconds in the stopping time, that's nice, but not the answer to this question. Right, so this question takes a little bit of fancy footwork, and I'll show you one of the methods today. All right, now let's look at the specs. All right, we got a mass. So this little shrimpy kid on the ice skating rink, he falls on his keister, and he starts sliding down the rink. His mass is 30 kilograms. All right, his initial velocity, that's about, 7 miles an hour. So he's going down there. He probably thinks he's, in the NHL, in the hockey league, but he's only going 7 miles an hour, so he's doing okay. For a little shrimpy kid, it's fine. All right, so you have the initial speed. You also have the friction force. Now, this one's important. And if you think about it, you've got everything here that you need to figure out a stopping time, but that's not what this problem is about. However, calculating stopping time is helpful at putting together the stopping distance, all right? Because with this information, you can also put down or put together a velocity graph. So make a note of that. And that is the strategy that I will give to you today. Construct a velocity graph, because we know that the area underneath the velocity graph between the graph itself and the time axis, no matter what the slope is, if it's an even horizontal graph or if it's tilted up or tilted down, you can figure out the area. That'll give you the distance. All right? So we can do that from this thing. All right? So let's look at a velocity graph. All right? And this is a slow down velocity graph. And it starts from an initial velocity. So it initially has 3.4. All right, so let me just mark that in up here. That's not unknown. Okay. I mean, you have to do this, you have to figure out, okay, if I'm going to make a velocity graph, I've got to have a few specs. That's one of them. The initial velocity, 3.4 meters per second in this instance. By the way, let me remind you on calculation problems, whenever you do a second attempt of a calculation problem, it's going to give you at least one of the numbers randomly chosen with a different value. And I think for this one, I'm not sure, but I think the mass of the little kid is the same, but the friction force and the velocity change. All right. So at any rate, you've got to read and figure out 3.4 meters per second for the example that I showed you. Now, you might have had 3.2 or 4.1 or something, but you're going to have an initial velocity. Now, the other part of the velocity graph that you need, I mean, if you start at 0, let me get my, I forgot to make my cursor gigantic. I better do that. Hold on, let me, gosh. All right, so this is better. All right, so, all right, there we go, nice and gigantic. So this, zero's over here. So, time t equals 0, that's easy. And it stops. So you're going to have a point down here somewhere out on the time axis. And that makes this a distance triangle problem. All right? But the problem is we don't know what this, from the problem itself, we don't know what that time is. But you can figure it out because it is the stopping time. All right? We've got a friction force. We've got some delta mv. No problem. We can figure out the stopping time. So that number over there, and that's actually the first thing that we're going to do. And it's the first thing that some of you did, I'm sure. And you got it marked wrong because you don't stop with the stopping time. You go one step further and calculate the area of this distance triangle. All right, we'll do that next. But first we got to do this baby. So F delta T equals delta P. Now we've got everything we want for that. We have a friction force of 19.2. And we have an MV of 30 kilograms times 3.4 meters per second. All right, now that 30 times 3.4, that's 102. All right. So we have 100, that's supposed to be kilogram meters per second. I put in a 2 there. Whoa, Dr. B. All right, so that should be 102 kilogram meters per second. I'll have to edit that, and it's correct on this line. So now to get delta T, the stopping time by itself, you divide both sides by that friction force, 19.2 newtons. Okay, and notice that I've changed it from capital N for newtons to kilogram meter per second squared. Perfectly fine. And the reason that I do that, as I mentioned before, is I like to be able to cancel units. So I can cancel kilograms, top and bottom. I can cancel meters, top and bottom. And I can cancel per second, top and bottom, but I still have a factor of per second in the bottom because it's per second squared. So that per second in the denominator becomes a regular second in the numerator. All right? And that gives me the time, 5.3. And I've just written out all the digits. It's not a bodacious calculation. All right? All right, so now we know what that number is here. You can write it down in your notes. 5.3125 seconds. So now we got a triangle, base times height times 1/2. Okay, so now we're walking in the park, hopefully. All right, so here's your base times height, 5.3125 for the base, and the height is 3.40, and I padded this one out with zeros. just so it kind of looks symmetric and everything, and even. And then that works out to 18.0625 meters. All right, but we're not done yet. We want to type it into the nearest tenth of a meter, but this is not the distance. This is twice the distance. Because remember, it's 1/2 base times height for a velocity triangle. All right, so here we go. Just divide that baby by 2. So 18.06 divided by 2 is 9.03. All right? So 9.03 meters to the nearest tenth of a meter is 9.0. And oh my goodness. Now check this out. Let's double check. This is the feedback from web courses. All right? Now watch what we got here. Up at the top, we got the score. Down the bottom, we got the answer that I typed in. And yep, right on the money. We got full dineros out of that one. All right, so there's your strategy, and that's an example. And you know what I think? I'll be giving you guys some homework this weekend. I'll give you a problem like this. I got a bunch that I can give you, and let you guys give it another shot. See if you can crush it. Because I know, Kisla, that you're going to, now that you've seen the major strategy, you're going to crush it. Okay? But let me pause for questions about this problem. Yes, Alexis. I divide by 2 because it's a distance triangle. All right? Base times height would be the distance rectangle. But this one's slowing down, so it's a triangle. And, so you gotta... And the other thing that you can do, I'll just mention it as a side note and in addition after Alexis's question is, you can figure out A if you want. You have delta V, now you have delta T. So you can go delta V over delta T, that gives the acceleration, whatever it happens to be. I don't know, what is that? 3.4 divided by 5.3. So can somebody calculate that out? It's going to be about 0.6 something or 0.7 something. 3.4 divided by 5.3. What do you get? 0.34? 64? Does anybody verify that? 0.64? Okay, so there's your acceleration. So then you can go 1/2 AT squared. All right? But if you remember, that's basically doing, Alexis, this triangle area. 1/2 AT squared is a distance triangle calculation. Right? So that would be the long way, figuring out the acceleration. This one is fairly easy if you think to make the velocity graph. But if you calculate, all the way around, it's like going the long way, going straight to Chick-fil-A or diverting. Why would you want to divert your path from going straight to Chick-fil-A? Especially at this time of the day if you haven't had lunch. All right? But if you go straight to Chick-fil-A. So this method is going straight to Chick-fil-A, Alexis. All right? And calculating acceleration, then 1/2 AT squared. That's like going to garage A and then back to the Chick-fil-A. Yes, you could do it, but if you apply superior strategy, you wouldn't need to. All right, so divide by 2, and here's the burn the answer. All right, now, no more questions. Let's go to collisions. And here's the thing that we want to emphasize. A collision, and we're going to work with boxcars on the railroad. Just like that old song. I've been working on the railroad all the livelong day, etc., etc. And what we're going to emphasize is when boxcars collide, there are no unbalanced external forces. All right? Now, this assumes, and you can make a note of this, in the case of boxcars on the railroad, it assumes that the railroad tracks are level. Because if the railroad tracks have a little bit of slant, then gravity's not going to be balanced. And you're going to have a vertical acceleration along the track. Right? So we don't want that. We're going to idealize it to a horizontal track. And we still have gravity. But what force balances the gravitation, the downward newtons of each car? What force balances that? I mean, if it's on a level track, you're not getting any vertical accelerations. And we know that there's weight force downward from the Earth. But what force balances that? Remember that? Remember that problem with the bowl of cherries? Yeah, the rigidity force. Okay, so you're going to have rigidity force exactly balancing the weight force, okay, if it's horizontal, okay? But if it's not horizontal, then the weight force will have a few newtons down, few downhill newtons, all right? And so the rigidity, so railroad tracks, they're always made out of something really rigid, like steel. You know, you never, I dare anyone to go along a railroad track and see if they've made a railroad track out of Jell-O. They just don't do that. They've never done that. They've never been tricked into doing that because Jell-O doesn't have any rigidity. All right? It doesn't even make sense. So no external forces that are unbalanced, but internal forces within the system of boxcars, yes. You know, the boxcars will bump into each other. You know? And so let's look at collision forces. And so they're interacting, it's an interaction force, and for this idealized horizontal track, it's going to be left and right, horizontal forces, okay? And because they're interaction forces, you know what it's going to be like? It's going to be like the two skateboarders pushing off. You know, whatever one pushes off with, the other pushes with the same size, but the opposite direction, okay? So let's look at this setup. We got 4 boxcars, and one of them's moving. Boxcar number 1 over here to the left is moving at 4.4 meters per second. Now the group, symbolized with the letter G for group, this group of 3, they're at rest. All right? All right? And when they collide, there are interaction forces. So those big, gigantic, you know, kind of hooks, you know, ultra heavy duty hooks that hook together the 2 train cars, that takes a lot of oomph to get those things to lock, right? You know, you couldn't do it. I couldn't do it. 10 of us could not do it unless maybe we had some levers and stuff. But boxcars, you know, they've got enough oomph that they can do it, all right? Now, what we're going to try to do is figure out the final state. And the final state, if you've ever watched freight cars or a train of freight cars being assembled, they'll just, you know, form a string. You know, they'll get 3 cars together, then they'll send in the 4th car and let it latch. And then they'll send in car number 5 and let it latch. You know, give it a little bit of motion, and just so it gets as far as, you know, the end of the string, and it latches in, all right? And so now, if it's just 4 cars like this, and they latch together, they're going to move off to the right, okay? You know, but they're not going to be going 4.4 meters per second, and that's what we want to figure out. How fast are they going? All right, here we go. All right. Let's start with this particular set of facts. Each one is 35,000 kilograms. Now that's going to cancel out in the end, so we don't really have to worry about it that much. All right, but we can write it down. And we can use that mass number, and that's about the mass of a fully loaded train car, or a box car. Okay, so this one's the one that's moving. So give it a velocity vector v1. Okay. And there are no external net forces, gravity and railroad track rigidity balance, so that's squared away. But we are going to have some horizontal interaction forces, okay? And they're going to be opposite directions. Let me ask you a question. When these things interact, which set of rail cars is going to push to the right? Boxcar number 1 or the group of 3? Boxcar 1. I see somebody up here in the front going like this. Yep, boxcar number 1. And so the group of 3 is going to give boxcar 1 a push back to the left. And guess what? If you're moving to the right, but you get a little bit of a push, a little bit of impulse to the left, you're going to slow down. And it's going to slow down to the exact speed that these other ones are going to speed up to. That's the way it works. It's kind of cool, actually, if you think about it. So let's figure out the total momentum of the system before interaction. So we're working this out in terms of momentum. P equals mv. Now we got a little bit of P equals mv from boxcar number 1. All right, so go ahead and write that down. 35,000 kilograms for the mass and 4.4 meters per second for its initial speed. So the multiple of those two babies together is its momentum. Now the other 3 are cinchi because they're at rest. All right, so over there, you've got 0 plus 0 plus 0, or as we said the other day, goose egg. All right? So the initial ding, 150. But is that correct? Can you verify me on that? 4.4 times 35,000? Is that good? All right. Okay, so 100, because, you know, sometimes I have a typo and stuff, but good. 150. Now, this has also got to be equal to the final. And why is that? And the final momentum is going to be the mass of all 4 of them. So 35 times 4 is, see, 35 times 2 is 70. 70 times 2 is 1. So this is going to be the total mass of 140,000 times whatever the new speed is. We don't know that yet, but we'll figure it out. Because the momentum has to be the same afterwards. So 154,000 kilogram meters per second to the right beforehand, before the interaction, and afterwards, they're going to be going different speeds, but afterwards you're going to have the same amount of momentum, right? So clicker questions if you please. Multiple choice. Here we go. Get your clicker on. Get your brain on. Why must the initial momentum of the boxcars, P subscript I, equal the final momentum of the boxcars? And if you've done your reading in chapter 4, I don't even want to look to get a show of hands. If you've done your reading, you know the answer to this. Or you can figure out your reading. If you haven't done your reading, I've caught you napping. What was that? All right. Yeah, see, look at that. Darian, we're going to have to regrade this after dismissal. I'll explain after class. let's just remember to, because we can change the question. We should have done a short answer for this one. Can you do it? Is it possible? Did we do it last time?
I can do it so all the answers have to be deleted out.
No, we don't want that. Okay, stop this question. Re-ask it. Okay, I'm going to hit the refresh key. Short answer. Hit the refresh key, then type in your answer again. Whatever you answered again, this way we'll be able to grade it properly. Now I want you to, when I go over the answers here, I want you to grade it. Okay, you'll see what to grade it. All right, good. I see most of you guys are typing in your answers. Okay, 20 seconds. Yeah, hit refresh key. Yeah, same question. Just so hit a letter and then hit the send key. Hit your letter and hit the send key. And this one actually, and you'll see here in a second. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Don't grade it yet. All right, but do display the results. All right. Now there's a big pile of you that voted for C. And there's another large-ish pile that voted for E. All right? Go back to the laptop, please. Now, this is the answer that I prefer. And I want you to write this down. Momentum is always conserved in a collision if there's no heat dissipation or friction or anything like that. So in this idealized interaction, or if you have things interacting out in space or inside of a vacuum or something like that, momentum is always going to be conserved. And even if there is friction and heat dissipation, you'll have fairly close to perfect conservation of momentum. However, this answer right here, they exchange equal but opposite momenta, that is actually kosher as well. And that is another way of saying Newton's third law, which is another way of saying that momentum is going to be conserved if there are no unbalanced external forces. All right? So this applies to the horizontal railroad track, but not the tilted one. All right? So you got to distinguish between those two. All right? So if you answer, roughly 71% of you selected a good answer, and we'll grade that accordingly. All right? Now let's get back to our calculation. All right, so the final momentum, P subscript F, is 154,000 kilogram meters per second, and that is because of conservation of momentum. All right. Now we've got a new grouping or a new set of boxcars, and they're all moving as one. Right? That's the way boxcars will behave. You know, if you get them all hooked together and give them a push, they'll all move off together at the same, whatever the speed is, you know, they'll each have the same one. For that reason, you can use the definition of momentum to rewrite the right-hand side of this equation. And that's just P equals mv for a different m and a new v. All right, now we know what the different m is. It's 140,000 kilograms. That's 4 boxcars, total mass. And they're moving as one object. All right? Because Alexis, they're all hooked together. So they're moving as just, you know, one big piece of steel with wheels on it. All right? And that's kind of an idealized view. You know, in reality, there'd be a little bit of rattle, but, you know, pretty much they'd move as one. All right, so let me move that up here to the top, a little bit out of the way. So there's our equation. And if you look at this equation, what do you see? Do you have a question?
No, I was just asking, like, I get that one is for all 4 of the boxcars.
Right.
I'm just trying to figure out why it directly
It goes directly because the momentum is conserved. So whatever we had initially, we also have in the final state. All right? That's the law of conservation of momentum. If there's no external forces, like if there's nobody, pushing something to the side or, pushing it forward or backwards or anything, the initial, whatever it was, and it was all in the boxcar number 1 initially. But now, after they hook together, that's fine. They've interacted, and they've exchanged momentum. But whatever they exchange, the total, what one of them gains, the other one loses. All right? Boxcar, here's a question for you. Which boxcar loses momentum as a single boxcar? The first one, because it slows down. All right? The other 3 gain momentum, but as a system, the total system is locked together now, and they're all moving at the same speed, and that's what we're going to figure out. So conservation of momentum tells us this, and then definition of momentum tells us this. All right? So this side is just from definition of momentum. All right? And if you look at that, you will see that you can get V subscript nu by itself. Nice. What's that? This one? 140,000 kilograms? For boxcars. Because the boxcars, they're identical boxcars, and each one is 35,000. All right, okay, good, yeah. So that's good? All right, yeah, that's what that one's. All right, so now if you don't have identical boxcars, it's going to be the mass of all the box. What this makes it, having them all identical makes the calculation a little bit easier. But you could have one at 135 and one at 134, 2 at 136, and it'd be fine. You can still do all the calculations. This just makes it kind of streamlined. In real life, a railroad train, they're not all the same mass. They're going to have slightly different. If they're all going to be loaded near maximum, but they're not, to the nearest kilogram. No, they're not going to be the same. But so this one's kind of, streamlined, so it's a little cinchy. This is how you guys don't actually work on the railroad all the live long day and stuff like that. So we're just going to make it a little easier. Anyway, so getting back to this now, you can see V nu. Just got to divide both sides by 140,000 kilograms. All right, here we go. There it is. V nu is equal to, that 154,000 kilogram meters per second divided by 140,000 kilograms. And notice that kilograms top and bottom cancel, but I'm left Vanessa with meters per second leftovers. I can't cancel those. But that's all right, because I want to have a velocity. I want to have a speed of some kind. All right? And you calculate that out. Anybody verify me? 1.1? Yeah, good. All right? Now, are you guys ready to try one of these? You want to try it? Let's try one. Let's see if you guys are ready to function at level 9, or we're still at level 1. It's a calculation. So hit the refresh key, and you're going to type in a number and then hit the send key. All right? Okay, so the calculation is to find V subscript nu, but now, and same 4 boxcars, but now the initial speed of V1 is a little bit faster, 6.4 meters per second. All right? And I'll give you a few minutes to do that. Can you turn the lights on? And definitely, as you're working through this, check with your neighbor, consult with your neighbor, et cetera, et cetera. You ready? We're doing a calculation here.
Yeah, is this the first one? How many did I miss? Two? That's fine. My car was stolen.
What?
Yeah.
What kind of car did you have?
A Camry.
You know what? Is that like the number 1 or number 2 stolen car in the United States? Because I heard like the number 1 is like a Honda Accord.
Probably. The reliable cars.
Yeah. Cars that everybody has that last a long time. That's terrible. You don't have low jack or anything?
I don't know what that is.
It's a car, it's a GPS.
No, I guess I don't.
So you're toast.
Yeah, I called my finance company because I mean I've made every payment on time, but I was like, for some weird reason, did you repo it? They're like, no.
Oh boy, I tell you. Okay, give me to the nearest tenth of a meter per second. So something 0.1 or something point something meters per second. You know what I did in my previous class? I had a Ricola, and I started, because I felt like I needed a little bit of a treat in the middle of lecture, and then I started garbling out my words because I had a Ricola, you know. Don't lecture with a Ricola. Unless, who's that famous Greek guy or Roman guy that he taught himself how to speak with stones in his mouth? Demosthenes or something like that? Aristophanes? Diogenes?
Is it M over P or is it P over M
For what?
for the final state? Is it the
Check your
for
notes.
the math?
Check your notes. The definition is P equals MV. Bruce, you got it? What are you doing over there? Organic. I tried to warn you. Stay away from chemistry, but no.
I don't really have a choice.
Yeah, I suppose. Yeah. Yeah. Organic chemistry, boy, I tell you, it's. All right, how many we got? 115. All right. 30 seconds. So type in your number, something point something, and then hit the send key. Make sure you hit the send key. Oh my goodness. What is that? Yeah. I see some answers that are looking a little unusual here. If you have a number, yeah, so there's two of you that must be working together. And if you have a velocity that is over 5,000 meters per second, that doesn't pass the plausibility test. So double check your numbers. You know what? Just trying to think, how do you get that particular number over 5,000 meters per second? Because, you know, and the reason I'm alerting you to that is on a test, you want to check your answer to make sure if it makes sense or not. it doesn't make sense to have something 5,000 and change meters per second because V nu, whatever it is, it's going to be smaller than the initial. I mean, because it's basically it's being shared with the other three, right? So it's going to be something smaller than 6.4 for sure. Okay. All right, 20 seconds. Starting now. $50 seconds. 10, 9, good, they got rid of it. 8, 7, 6, 5, 4, 3, 2, 1, 0. All right. Raise your hand if you answered 1.6. Sweet! 84% of you did. Good. All right, so there's your answer, 1.6 question.
For this kind of problem, why can't we just divide 6.4 by 4?
Katie, you just gave me a good question. For this kind of problem, why can't you just divide 6.4 by 4? And the answer is, for this kind of problem, where I've made all the boxcars identical, you actually can. But if any of the boxcars are not identical, then it's a little bit trickier. But you still, you know, the thing is, it's still fairly easy to do, you know. But yeah, that's you've discovered, Katie, you've discovered my secret trick. So that, you know what that means? The test, if I ask you a question like this, it's going to have to be hard. It's going to have to be unequal boxcars. Now that you guys know one of my secret tricks. All right, so let's go over this concept now. We've done some calculations. Skateboarders exchanging momentum is another one. Now, the initial momentum of that system is equal to 0 because they're both at rest. You know, in the demonstration that we did here in the lecture hall, right? And they pushed off. One of them got some velocity. The other one got a different velocity. They both got the same amount of momentum, but they're opposite but equal momentum. So those two momenta add up to 0. Right? So it's like a repulsion. The total momentum, and here's the basic idea. The total momentum of a group of interacting objects remains the same in the absence of external forces. All right? So the boxcars hooking together is not an external force. That's an internal. That's internal to the group of boxcars. Okay? So this one, this sentence here, number 2, is why I insisted that it be a horizontal railroad track, because if it was tilted, then you wouldn't be able to meet this. You could still figure it out, but it'd be a little trickier. All right? So conservation of momentum. Now, I'm going to start teaching you some of the theory of relativity now. It is now time to do that. It is now a perfect time to teach you about the 4-dimensional structure of space-time. And this was one of Albert Einstein's key principles, his key doctrine. That the universe is not just 3 dimensions, and then time is this thing that everybody agrees about. You know, if they synchronize their clocks will always be synchronized. He said, no, the universe is a fundamentally 4-dimensional structure, and time is a little bit different, but you treat it as if it were a 4th dimension. In fact, time is the 4th dimension. So in the 4-dimensional view of the universe, the 3 spatial dimensions, we call it, X, Y, and Z, Or, if you're in spherical coordinates, latitude, longitude, and then the distance away from the center of the Earth, or altitude above the surface of the Earth, that'd be 3 spatial dimensions. And there's one temporal dimension, time. Right now, that's the one that's mysterious. And 113 years ago, Albert Einstein said, if you treat time as a dimension, you handle it slightly differently, but it is a dimension. It's a cousin. It's not like the difference between a grape and a hammer. It's like the difference between a grape and a strawberry. They're cousins. They're both. So here's an example. Up here in the front, we have this lectern up here. This table, right? And so if you consider in this picture, now normally for left and right across the front of the room here, I always say that's the x-axis. But for this diagram, we'll make that the y-axis. And then the x-axis will be out towards you guys. Right? So and then the z-axis is the one straight up in the air towards the zenith. All right? So those are the 3 spatial dimensions that we normally talk about. And you can label them differently. Like you can make the y-axis, you can call that x, and then you got to call the z-axis the y-axis, and then you got to call the x-axis the z-axis. But they all have to go in a rotation, x to y to z. And so this is how a physicist would do it. Because in physics we usually use z for the altitude coordinate or the elevation coordinate. Now, and then the temporal dimension, there's no way to draw a 4-dimensional set of axes. We can't really, we can't do a 4-dimensional, not even in perspective. Now we can do another 3-dimensional. Here's one thing that we do a lot, and that is in relativity, we draw like a 3-dimensional perspective view, and one of the axes is time, and then the other 2 are spatial dimensions, and then we ignore the 3rd spatial dimension. Then we can do a perspective view. The dynamical quantities that encode interaction and potential for interaction are 2. The first dynamical quantity is momentum that we've just been working with. And momentum is defined as the mass of an object times a spatial velocity. Right? So what I mean by that is it's P equals mv, and the vector v can have an x component, a y component, and a z component. Now normally what we do is work with an x component only, horizontal back and forth. But we have talked about a baseball arcing up and a baseball arcing back down, and that one has an x and a y velocity component. And in general, you're going to have 3 spatial components for a spatial velocity. So the momentum is also what we would call, it would also have spatial components. So the momentum could have something along the x-axis towards the back of the hall, the lecture hall, a y component along the front, left to right across the front, and a z component of the momentum towards outer space or down toward the center of the Earth. Okay? The second dynamical quantity that encodes interaction is called energy. And you've all seen probably this famous formula, E equals mc squared. Energy is equal to the mass of an object times the square of the speed of light. That's one of Einstein's most famous equations. And there's many other forms of energy than that one. And what we're going to be working with is some forms of energy called kinetic energy and potential energy, gravitational potential energy. All right, so let's look at these three spatial dimensions again. All right, now we have x, y, and z. Here's how you would express the momentum. P equals mv. So there's the x component of P, the y component of P, and the z component of P. And so, you know, in general, you know, if you hit a baseball and there's any spin on it, the baseball won't just follow a straight parabolic arc up and down. It'll actually, especially if there's any kind of wind, it'll follow a parabolic arc and kind of curve to the left or right. Or if it's got topspin on it, it'll break out of a parabola and it'll kind of shorten the flight a little bit. All right, so if you got spin on a baseball, you'll have to deal with all three components. All right, now that's the momentum, that's the spatial momentum. In space-time, we work with four-dimensional vectors. Okay, and this is what we're going to start studying on Tuesday. Space-time position. Time is actually the first one that we list, and then the three spatial dimensions. And then energy momentum, we would call this the energy momentum vector. And energy, whatever it works out to be, you know, kinetic energy or electrostatic energy or something like that, is the first part. And then the three spatial ones come after that. All right? And I'll just give you a little bit of a flavor of how this works. In spatial coordinates, x, y, and z, Pythagorean theorem rules. But in 4 dimensions, there's a significant change. Instead of 3 plus signs in Pythagorean theorem, there's 2 plus signs and a minus sign. And that's the difference. And we'll start talking about that on Tuesday. So you're dismissed. It's 1:09. I'll see you Tuesday. Look for some homework over the weekend, just a few small ones. Hey.